Any problems with assignment and contents? Everything going fine? Did anybody get a chance to go through the homework solution? Does that seem right? So go through it, check whether it's correct or not. We have already started reading the homework. We will done by today or tomorrow. Okay, so let's continue with our discussion on function frames. So we are seeing how do we manipulate the stack when we call a particular function. We saw some examples, but we didn't really fully understand how or what is the rule or what are the methodologies that the runtime execution engine is using to manipulate the stack. We didn't really understand. But today what we'll do is we'll define some rules as to how the stack should be manipulated and see whether those rules are exactly manifested in practice or not. So that is the purpose of this exercise. So when we are talking about function frames, we are basically talking about the methodology taken to call one function. So you have a main code, and from that main you are calling a function foo. What happens to the stack? How do you call a function? That's what we are trying to do. Now there are many different things that needs to be done when you call a function. First of all, you need to tell us where is the return value. The function executes, gives you some output. Where is it stored? Where do I go and check it? The second thing is the function has input parameters. How do I let the function know that I want the specific input parameters? How do I let the function? That is the second thing. The third thing is we know that each function should have a particular portion of the stack. That particular portion is called function frame. Every function has its own stack. Right? So how do I let a function know that your particular frame is corresponds to a particular area in the stack? How do I let that function know? What is its frame pointer? So frame pointer is the pointer that stores the first line of stack where it can put variables. Then we also have to have the return address, which means that after we have done executing the function, what is the next line of code that we should execute? So after the function returns, what is the next line of code? So return address, we should give the return address. The fifth thing is that the function will have local variables. How does the function manipulate local variables? How does it use the stack to manipulate local variables? And the last thing is that the function has temporary variables. Temporary variables means the function might do a plus b plus 1. Where do I store that 1? Right? So all these things we need to do. Now there are two entities here. First entity is the caller, the function that is calling another function. And the second entity is the callee. It is the function that is being called. Now the responsibility of all these have to be divided among these two. Now how do we divide this responsibility? That is the calling convention. That is the calling convention, and it is different for different runtime execution engines. We will talk about the x86 calling convention. So what is the calling convention? Who should store all the previous information that we have decided? Is that the callee or the caller? We should have some distribution of responsibility, right? So this is the distribution of responsibility for Linux x86 calling convention. So what does the caller do? The caller has to do these steps in order. It has to do it in order. It cannot go out of order. So first of all, it should push the arguments onto the stack in reverse order. So if a function needs x1, x2, x3, the caller will do x3, x2, x1 and upload that into the stack, or push that into the stack in the reverse order. Why do you do in the reverse order? Can you give me a reason? Can you think of a reason why do you upload the variables in the reverse order?
First in, last out.
No, that is how you are manipulating the stack. First in, last out.
Usually
But
you use the first. So when you pop, you're going to have the first one.
no, that's fine. I can pop in a different way. Pushing, popping is in my control, right? I could have pushed in from left to right and still popped in a different way and get the arguments.
Convention.
So why, every convention has a reason. What do you think the reason can be? Any idea? What can be the reason? The reason is not really related to whatever we are discussing here. The reason is whenever you compute, whenever you are computing the values of an expression, whenever you are computing the values of an expression, typically you compute from the right. You start computing from the right, go to the left and have a value. So in order to mimic that, in order to facilitate that type of computation, where you go from right to left, the caller uploads the variables in that manner. Why you do that? Because when you are computing from right to left and you see that there is a error, so error may be in type, or error might be in wrong usage of an operator. So if you have an error, then that means you don't have to go and parse the entire list of arguments. You can stop and do a syntax error, a syntax or semantics or whatever error you want. But if you go from left to right, you don't know the error until you have parsed the entire operation. So that's why when you go from left to right, you have to parse the entire expression and then find out that there was an error in the operator. But if you go from right to left, you don't need to parse the entire expression. You can know that there is an error by just parsing in the middle, or by partially parsing the expression. So that's one of the reasons that the caller pushes the arguments onto the stack. It's not really related to whatever we are discussing, but it's good to know. So that is the first thing the caller does. The second thing the caller does is it has to push the address of the instruction after call. So you call the function. Now what instruction will you execute after calling? You have to push that into the stack. So that is the function of the caller. Right? Now what do the callee do? The callee pushes the previous frame pointer onto the stack first. It has to take the frame pointer, the previous frame pointer, not its own frame pointer. It has to take the previous frame pointer and put it onto the stack. Then it creates space on the stack for local variables. So what is the frame pointer again? Frame pointer signifies the first line of code of that particular function. Okay. So it pushes the frame pointer onto the stack. It creates space on the stack for local variables if it uses any. If the function uses any local variables, it creates space. It ensures that the stack is consistent on return. So whatever changes it did to the stack, creating space in a stack is not a change. It does not really change the stack. What changes the stack is pushing things or popping things. So if you have pushed or popped certain things, the call should reverse those. Right? There has to be a way to reverse that. then it has the return value put into the EAX register. So these are the 4 responsibilities of the callee, and there are only 2 responsibilities of the caller. Now then, what we did last class, we looked at this example. This example has all these instructions. We didn't really understand why, and we understood a little bit as to what are these instructions, but did not really discuss in detail how the caller and the callee are executing their responsibilities. Right? So what did we understand from this code? We understood that the callee is doing push AEBP, right? So push EBP means it's doing something with the frame pointer. The frame pointer is an EBP, the base pointer register. So it is doing something with the frame pointer, that is saving the frame pointer in the stack. It's doing something like that. Then it is moving the ESP to EBP, which means now it is taking its own frame pointer and storing it into EBP. It is doing something like that. Then it's doing all the computation, and finally it's popping EBP. Why is it popping EBP? Because it's trying to reverse. It's trying to manage the stack. Because it pushed EBP, so that means it's changed the stack. Now it's popping it so that to reverse the change. Right? So it is doing some of its responsibilities. But then there are several other responsibilities. For example, putting up the return address into the stack, then clearing up whatever changes you made into the stack when you are returning from a function. All those things we didn't really discuss. Now let's discuss those things. So now what we'll do is we'll take this code and see exactly what is happening in the stack, because some details are hidden in this call and return function. A lot of details are hidden in this call and return function. So we'll see what details are hidden. So let's talk about that. So we have this program, and we have given the addresses to all lines of code. Unless you have the physical addresses to all lines of code, you cannot execute a program. So you have to have those lines of code. Now let's see what happens to the stack. So let's say we have this stack, and these are all the registers. Now the first thing we need to know is that when we call main, some other process is actually calling main, right? So that some other process will have its own frame pointer. What is the value of that frame pointer? We don't know. Some arbitrary value. Now let's assume that the current status of the stack pointer is that FD2D4. Let's assume that that is the current stack pointer. Let's assume. So if we assume that that is the current stack pointer, then this stack pointer has to be more, or has to be greater than the frame pointer. Why? Because the previous program might have done something to the stack. If it didn't do anything to the stack, then at best stack pointer will be equal to the frame pointer. At best. It cannot be less than the frame pointer. It has to always be more than the frame pointer. Because remember what we did? We took the stack pointer, made it frame pointer, and then whatever manipulations we do into the stack pointer, it is manifested in the stack pointer. So the stack pointer changes, frame pointer remains the same. And so frame pointer says that that is the start of the function frame. So there is the start of the stack where the function can manipulate the stack. Right? So there is the start of the function frame. That is what frame pointer gives. So that's why let's assume that the function did something to the stack. The function which called main did something to the stack. So that's why let's say the frame pointer of the previous function is some value less than the stack pointer. So now what main does? Now main is the calling here, because some other function, some other process has called main. So since main is the callee, one of the responsibility of main is it has to push the previous frame pointer into the stack. So what was the previous frame pointer? Where was it stored? It is stored in the base pointer. a base register, sorry, EBP, right? So it pushes EBP. So if you push, what was the convention of pushing? You first decrement the stack, and then you put the value into that memory. So you decrement the stack. So stack became before we do that, we have to also initialize the instruction pointer. The instruction pointer is what? Is the line of code that you are going to execute. So instruction pointer is set to 80483A5. Right? Now once it is set, let's execute push EBP. So EBP, we are assuming that, let's say EBP has a value of FD2C0. Let's assume. So now when the moment you do push, then you what you do is you decrement the stack pointer. So stack pointer became FD2D0 instead of FD2D4. So decrement it, and now you put EBP, whatever EBP has value in that memory location, FD2CD. Right? That is what you did when you did push. So now since you have executed, you have finished executing push. So what you do, you increment the instruction pointer. So you increment the instruction pointer, EIP. So now you are executing the next line of code. What is this next line of code? This is moving the current stack pointer into EBP. What is the current stack pointer? The current stack pointer is the start of the function frame. Which function's frame? Is the main function's frame. So which means that whatever is after that blue line, that's where main can do whatever it wants. Right? That's the stack of main. At this point, all this is the stack of main. Right? I can write whatever I want. Local variables, addresses, whatever I want I can write. So that becomes the stack of main. So that is the function frame of main. Right? That is the start of the function frame. So main has to store the first address. That is a responsibility of the callee, because main here is now callee. It hasn't called any function yet. So some other process has called main. So main is the callee. So main has to store its own frame pointer. So that is the purpose of the next line. Move ESP to EBP, which means whatever was the value of ESP, that's the start of the function frame of main. So you put it into EBP. So now EBP remains the same. You don't touch EBP. Don't change EBP now, because EBP now points to the function frame. Now what you can change is you can change the stack pointer. You can vary the stack pointer, but you cannot vary the EBP. Now what is the next thing that the program does? The program increments instruction pointer. Now this fact we discussed last class, that instead of incrementing by 1, it incremented by 2, which means it incremented by 2 lines basically. Why did it increment by 2? Because we know that some instructions take more space. For example, a subtract instruction takes more space. It's not the same as move. Move is a 1-line code. Subtract instruction is a 2-line code. Right? So when you learn assembly programming, if you convert sub into hex, you will see that instead of 32 bits, it is 64 bits. If you convert sub into hex, but move is 32 bits. So each instruction has a different size. Every instruction has a different size. For example, if you look at NEA, right, move and NEA in that callee, you will see again from 48398 going to 4839D, right? So B, C, D, three lines. So NEA is much larger instructions. So instruction sizes vary. That's why instruction pointer increments vary. So you increment instruction pointer. Now what is the next thing that you are doing? You are subtracting the stack pointer. So you're changing the stack pointer. Why are you changing it? Because now you want to create space for local variables, right? Now, not only local variables, you want to also create space for the input arguments of the function that you want to call, right? So you have to push those arguments into the stack. Somebody has to do that. Who does that? The caller does that. So now main has changed roles. Main now becomes caller. Main is now calling that calling function, right? So main has changed roles. So what is the responsibility of main now? The responsibility of main is it has to push all the input arguments of the function callee into the stack. So how does it do that? First, it creates some space. So how does it create space? It declares the stack pointer. So stack pointer instead of fd2d0 now becomes fd2b8. If you do minus 18 means how much? 24, right? In decimal. So if you do minus 24, that should be the fd2b8. I might be slightly wrong in subtracting. You can check. So if that is the case, then fd2b8 is there. Stack pointer changes to that, right? Then you go to the next instruction. What you are doing? You are taking the number 40. Right? You are taking the number 40 and putting it in ESP plus 4. So what is ESP plus 4? Basically FD2BC, you are putting it there. Right? Now you again increment the instruction pointer, and you are now moving the number 10 into the top of the stack, ESP. So which means that one became ESP. Right. Now we have some problems because now we did not discuss what call does. So the next thing we will do is call. Now call goes from when we go to call, we first increment the instruction pointer. Now we want to execute call. Now notice that how we execute call, we give the address of the first line of code for calling, right? We give that address. So what is the first line of code? Is 8048394. So we are calling that. Now what do we do next? We are decrementing stack pointer. Why are we decrementing stack pointer? What was the responsibility for calling? What was another responsibility of calling? The return address. Right? Return address means what is the next line of code I should execute. So one of the responsibility of caller was that whatever is the next line of instruction that you want to execute, you should push it into the stack. Right? That is the responsibility of caller. Now this thing we didn't discuss last class, and that is hidden in call. Whenever you execute call, the first thing call does is pushes the next line of pushes the address of the next instruction into the stack. So what is the next instruction address? It is 80483BF. So what it does now is it decrements the stack pointer and pushes that address into the stack. So now ESP became FD2B4. Your stack in that the top of the stack has the next instruction that we would execute after returning from calling. And now notice what did instruction pointer become? Instruction pointer takes the argument of call. What is the argument of call? Is the address of the first line of code that will execute in function callee. Right? So call has all these, call does all these things. So a lot of things call did. We are not done yet with call. The next thing call does is that it takes that program counter and puts it there. Why does it do that? Because the instruction pointer is there. So these are all the things that call does. So what is the first thing that call does? We can reiterate. This is important because in the exam we will tell you to trace the what happens to the stack. So you have to understand this. So first thing is we change the instruction pointer. We are executing call now. The first thing call does is that it pushes the next address. Pushes the next address into the stack. So if it does that, it has to decrement the stack, put the value into the place, to the top of the stack. Then the next thing it does is that updates the instruction pointer. Updates the instruction pointer to the to the address of the first line of code of calling. And then so once you have that in instruction pointer, basically the program counter directly goes there. Right? So these are all the functions of call. The call does that. Now the caller's responsibility is done. It has pushed all the input arguments into the stack. It has also pushed the instruction, next instruction that it wants to execute after you return from callee. It has done all that. So caller's responsibility is done. Now we come to callee. Now callee has 4 responsibilities. The first responsibility is it has to take the previous frame pointer, put it into the stack. Right? That is the first responsibility. So that is what it does. It pushes EBP. What is the stack pointer now? Stack pointer is FD2B4. So if it wants to push it, it has to decrement the stack pointer. So it decrements the stack pointer. It becomes FD2B0. That is FD2B0. Reduce. To push the base pointer. Base pointer is FD2D0, which was that pointer. So that was the start of the function frame of main. So we put that here, right? So that is the first responsibility. What is the second responsibility? Store its own frame pointer. That is what it does with the second line of code. Move the stack pointer now into the frame pointer. So what is the stack pointer? The stack pointer is FD2B0, right? So you move that FD2B0, you move it into base pointer. So base pointer becomes whatever stack pointer is. So now, if callee wants to manipulate the stack, it can only manipulate up this onwards, FD2B0 onwards, right? So that becomes callee's function frame. Now what it does, it executes the next line. The next line is what? Move C to EAX. So now before we go to that line, 2 responsibilities, actually, yes, 2 of the responsibilities are done. First of all, I have taken, the callee has taken care of the previous frame pointer, and callee has taken care of its own frame pointer. So 2 responsibilities are done. So then you move, move on with the computation. So you say that EBP plus C, right? So what was EBP? FD2B0. So so now since EBP, so you can execute or you can access anything that is from 0 to 8 onwards. Callee can change or can push new values only after the stack pointer, right? Callee can access all those variables, that's fine, but callee can only put variables or things into the stack after this point. So this part is Colley's function frame as well as these three things, because these are input arguments of Colley. These are input arguments of Colley. That has main has done that. But Colley cannot access any of those variables because those are not part of the input arguments, those are part of main. So now we have, by just putting in input arguments and manipulating the stack pointer, we have divided the entire stack into two parts. One is main's function frame and another is Colley's function frame. So Colley's function frame is what? It includes whatever is below stack pointer, and it also includes whatever are the input arguments. Right? So that point, up to that point, was input argument of Colley. So this is the entire function frame of Colley. After that, on top of 40, Colley cannot access because that is not neither the input argument nor the stack pointer. So that is part of main's function frame. So at this point, by just doing the initial responsibilities of Colley, the first two responsibilities of Colley, we have partitioned the entire stack into two parts, two function frames. One is the main's function frame and there is the Colley's function frame. Now we move on and try to do the execution. Now is this clear up to this point? If you have doubts, you can ask me questions later. Now, okay, now what happens if we move EBP plus C to EAX? What is EBP plus C? EBP plus 4 is this, plus 8 is this, plus C is this, right? So we have 40. So in EAX we have 40. Then we do move 8, EBP plus 8 to EDX. So EBP plus 8 is what? EBP plus 4 is this, plus 8 is this. So 10, we move 10 into EDX. Right? Then we execute the next line of code. So LEA, EDX, EAX, and we put the results into EDX. So basically we add these two. 28 plus 8. How much is that? 40 plus 10 has to be 50. So it is 32, right? In hex. Yes. So in EAX we have 32. You understand why it is 32, right? Just add them up and represent in hex. So we did all those, then we add 1 to EAX, it becomes 33. We are done with the computation. What is the instruction pointer? Instruction pointer is 80483A0, which is the current line of code that we are executing. We are done executing, so we will have to go forward and make it A3, right? We are done executing 80483A0. Now at this point, when we are doing all those computations, we didn't change anything in the stack. We didn't do anything in the stack. We didn't do anything in the EBP also. So EBP and stack remains the same for now. No changes. Now we are done computing. So we have to do. We have to finish our other responsibilities. So what was the third responsibility of Colley? The third responsibility was whatever changes you made to the stack, you have to reverse. Right? Now, what changes did Colley make?
Okay.
No, it did push EBP. Right? It did do push EBP, and also it made changes to the stack point, to the base point, frame pointer, right, or base pointer. It made those two changes. So first of all, it has to revert that. So if you do push EBP, you have to do pop. So Colley does pop EBP. Now if you do pop EBP, then what is the first thing that you do? You take the value at the top of the stack. Top of the stack has value FD2 D0. So now EBP becomes FD2 D0. Because previously FD2 B0, it became FD2 D0, which is that top address, right? FD2 D0. Now after you take the value, put it into EBP, what you do, you have to increment the stack. Oh, so that one became the EBP. you have to increment the stack. So stack became FD2 B4. So you go up, right? So that is the entire push or pop. Sorry, entire pop execution. So now you have changed the EBP, reverted it back, and also you have reverted back the stack, right? So by just doing pop, you did two things. You popped into EBP, so whatever change you made to EBP, you made move ESP to EBP, you made that change. So you reverted that change by popping. And also by popping, you changed back the stack pointer, right? ESP. So pop serves these two purposes. Now we come to return. Now this is another important instruction. There are a lot of hidden things here. So let's go one by one. What are the hidden things here? So now let's take a snapshot here. What happened? EAX was 33, EDX is 10, ESP is FD2 B4, EBP is there, FD2 D0, and my next instruction pointer is 804838A4 because I haven't executed return. Now what happens next? What happened? What happened was EIP changed. How did EIP change?
Once that next instruction on me.
What?
Back. Just goes back.
How does it go back?
Pop.
You have to pop, right? You have to pop the stack. You pop the stack. See, in the stack you have 80483BF. This instruction, this address you have. How will you get that address? Just pop the stack. So that address, you pop it into EIP. So pop EIP. That instruction is embedded in return. We don't explicitly state that. So what I am doing is now taking that 80483BF, putting into EIP. Then you see ESP is incremented, FD2B8. So ESP goes up. So return has one component which says you pop into EIP. That is hidden inside return, right? So now if you change the EIP, what you do? You just come back here, right? So by just popping, what you did was, remember when we called, our stack was exactly that. Right? That is what our stack was when we called the function. So what happened here is now the stack came back to what it was before calling. So by using that return, we have reversed whatever we did before we called. Right? So our stack now is the same thing, but what has changed? The return value is in EAX. That is the only thing that has changed. So what we do is we take that return value and we put it in EBP minus 4. So what is EBP minus 4? It's FD2 D0 minus 4. We put it there and then take EBP minus 4 and put it into EAX. Why it does that twice, I have no idea. It just does it. Right? I have no idea why it does. And nor does anybody. Then we execute the instruction leave. Now what happens when we do leave? So leave and return, these two things we have to understand what happens. The first thing that happens when we do leave is from FD2 B8, the stack pointer becomes FD2 D0. How did that happen? So that is inside leave. So whatever changes main did to the stack, it decremented stack pointer by 24, right? That's what main did. When you execute leave, that operation is reversed. So you go back to the stack FD2 D0, which means the frame pointer you move the frame pointer into the stack pointer. So previously when we were calling main, you move the stack pointer into frame pointer. Now when you are doing leave, you take the frame pointer, move it back to the stack pointer. Right? So now it became when you do leave, stack pointer becomes FD to D0, so it goes back there. Frame pointer becomes FD to C0. How? Because you pump the stack again. Let's reiterate this. Why did this happen? We are executing leave. What did we do when we called main? Main is what? Main is a callee now. And the caller was what? Some process. Right? Now, what is the responsibility of the callee when it returns? Same as what we have seen before. It has to revert whatever it did to the stack. So, which means it has to do pop in. No, it has to revert the stack, whatever it changed. So the thing that it changed was it subtracted the ESP by 40. Right? It subtracted the ESP by 40. Now, how can you revert this change? So remember, when we first executed, we did move ESP to EBP. What was ESP? When we first executed main, the second line of code of main, what was ESP? ESP was the stack pointer of the previous process, right? And that's where the frame of main started. It was the stack pointer of the previous process, and that's from where the main the frame of main started. So we had already stored it. We had already stored it to EBP. So if you now leave, what leave does is that it takes EBP and moves it into the stack pointer, SP. So if I do that, then that means I'm reverting whatever I changed to the stack. Do you understand this? What leave does? Reiterating. What leave has to do, the responsibility of leave is whatever you made changes to the stack, you have to revert it. How do I revert it? I know that the second thing that I did was I took the stack pointer, the current stack pointer, put it into the base pointer register. So I have the whatever, or I can easily revert whatever changes I made to the stack pointer, just taking the base pointer and copying it back to the stack pointer. If I do that, then I will just revert it back. So that's what leave does first. Then what it has to do? It has to maintain, or it has to also maintain the frame pointers of the previous process. Right? So how does it maintain the frame pointer of the previous process? Now it knows that what is the first line of code that I executed. The first line of code that I executed was I did push EBP. Push EBP means what? Means I took the frame pointer of the previous process and I put it on stack. So if I pop, then I reset the frame pointer. Do you understand? That's the first line of code main executed, push EBP. So which means I took the frame pointer of the previous process and put it into the stack. Now I have already reverted the stack. So stack pointer is back at what it used to be previously. So if I pop the stack, then that means I will get back the frame pointer of the previous process. And that is what I need to do. So leave also pops the stack. So you pop the stack. Once leave pops the stack, what happens is that EBP becomes a FD to C0, right? EBP becomes FD to C0, and you increment the stack pointer. So stack pointer becomes FD to D4, right? The stack is back to what it was before. Right? The base pointer has the frame pointer of the previous process. The stack is back to FD to D4. Now you just return, right? So when you return, what you do is you change the instruction pointer. This return is the same instruction as the callee return. So that is the entire execution. So now do we understand how the responsibilities of the caller and callee are taken care of? Is it confusing? Is it do I need to go over everything again to make it more clear? Do you have any question? Yes.
How the in the main function you put the value 0x28 and 0x8 stack, and when you jump into callee, how do you know your position? Like it's a 0xc plus EBP and 0x8 plus EBP. How does it know that?
Okay. So how does it know that it had the values are in EBP plus 8 and EBP plus C? How does it know that? That's a good question. So what is this question? Reiterate. Main moves these variables 40 and 10 into ESP plus 4 and into ESP, right? So some portion of the stack is there. Now you go to callee. How does callee know that I have to do EBP plus C to get the first argument, and I have to do EBP plus 8 to get the second argument? How does callee know? What is the rule? You have to see. What is the calling convention? Callee knows the calling convention, right? That is known to all functions. So the calling convention is you will put the arguments in the reverse order. Then the second thing you will do is you will put the next instruction pointer into the stack. And then you would also you put the next instruction pointer into the stack and you will come to callee. Right? Callee knows that because that is the responsibility of caller. That is known. So you know that at least one of the top of the stack has the instruction pointer for the next line. You know that. The callee knows that. The top of the stack has the instruction pointer. The second thing callee knows is that callee itself has pushed the frame pointer into the stack. So callee knows that now the top of the stack has the frame pointer, and the next item in the stack has the instruction pointer. Now after that, whatever is in the stack is my arguments. I know. By knowing the calling convention, callee knows that the first two items in the stack are the frame pointer of the previous function and the instruction pointer which holds the address of the line that I will execute after returning from callee. So I know that the first two items I cannot use, right? Then if callee knows the calling convention, then callee knows that after those first two items I have my arguments. So that's why now callee also knows that I have two arguments, not just one. I have two arguments. So the first argument I know the caller has done from right to left, right? The caller has done from right to left. So to get from the left one, I need to increment further twice. I need to increment the stack by twice. So that's why I need to increment by, I need to first increment by doing by adding 4 to ESP. Then I add again 4 to ESP to remove those first two items. Then I add 4 and another 4 to get the first argument. So I have to add 16 to ESP. Now I didn't add 16, I added 12, but then I added to EBP. Right? So EBP plus 12 is same as ESP plus 16. Now whenever I execute some code, I do not refer to local variables relative to stack pointer. Why? Because stack pointer can change. I only refer to variables relative to the frame pointer. That is the first thing we talked about maybe 2 classes back. So you have to have the frame pointer because you refer to variables with respect to the frame pointer, not the stack pointer. So in this case, stack pointer plus 16 is the same as frame pointer plus 12. Why? Because you have decremented the stack pointer once by doing push. So that's why I need to do EBP plus C. So that's how Collie knows. If Collie knows calling convention, then Collie exactly knows where are the local variables. Any other doubts? This will take a lot of time to assimilate. What you do is you go home and think hard about this. Just follow the sequence of what are happening, what all the things are happening, and try to reason. How do you reason? You follow the calling convention. Exactly follow the calling convention. And literally try to analyze what is happening following the calling convention. Then you'll surely understand. So you assimilate, try to assimilate this. If you have problems, you can ask me next class. We will move on. Right. So now one of the important things that we saw is we are passing parameters. How did we pass function parameters here? We pushed the values onto the stack and we pushed it in the reverse order. That's fine, but we pushed the values onto the stack. Now, what are the semantics of passing parameters to a function? There can be multiple approaches. So we will now talk about these three concepts: pass by value, pass by reference, pass by name. You might be familiar with all of these. And how many of you know about pass by value, pass by reference, pass by name? What does C do? Yes? It can do both. It can also pass by value. You can pass a pointer as argument to C. You can also pass a variable as argument. Does it do pass by name?
Forgot what that is.
That's Java.
Nobody does pass by name. Right? Pass by name is a very weird thing. We'll talk about pass by name, and it can have like totally mind-boggling results when you do pass by name. So we'll talk about each of these. What is passed by value, what is passed by reference, what is passed by name, and so on. So let's discuss what is passed by value. So what is it? Values of the actual parameters of at function invocation are calculated, then copied to the function. So there are two concepts, right? There is the concept of actual parameters. What is actual parameters? Is the input arguments x1, x2, x3. Right. So, and there is the values of the actual parameters. Values of the actual parameters means the instances that you are using. So if you say if 1, 2, then 1, 2 are the values, and x1, x2, which were the input arguments of the actual parameters of the function. Right. So values of the actual parameters at function invocation are calculated and then copied to the function. So C does that, right? Just the copying of the values onto the stack. That is how we did for that is passed by value, right? Just the example that we saw just now, where we push the values into the stack. That is passed by value. So let's take an example. Oh, already know the results. There's some problem with the animation. Anyways, so if we have this pass by value, this function, then we get the result 9 and 4. Right? How do we get the result 9 and 4? It's because we are passing by value. So when we do test y, we take the value 4, put it into the stack, right? If you do that, then test 4. So when we do test, we then pop the value from the stack, we get 4. So x becomes 4, x plus 5 becomes 9. We print that 9. Then when we come back, we remanipulate the stack and remove that input arguments. Then y becomes 4. So we print 4. So 9 and 4. That's how we get the result. Now if we do the box and circle diagram of this, then what happens? We have initially we have a y in main, we have the value 4 in it, and when we go to test, since we have that int x is a local variable in test, right? There is a global int x, fine, but there is also a local variable. So we consider that as a local variable, that is the scope. So so int x has the value 4 because we have done test y, and now int x has been converted to 9, so you print 9 and 4, right? And once you get out of test, that x is gone because the scope is gone. Okay. So that's how that the box and circle diagram. That's pretty simple. Now let's talk about pass by reference. Pass by reference, the formal parameters are bound to the locations associated with the actual parameters. So now what are the formal parameters? Formal parameters are the values that you are using to call a function. Right? So test y. So here x is the actual parameter, y is the formal parameter. Right? Because y is the parameter that you are calling with. So the formal parameters are, I think I switched it. Anyways, it doesn't really matter. So the actual parameters must be L values. So whatever you're calling with has to be L values. So if you have this code, so you know that test has a pointer. It takes a pointer. Right? It takes an address x, int ampersand x. Now you have the same code, but just that difference, int ampersand x. That is the only difference. So let's. What will be the output? Turns out that the output becomes 9 9. How did it happen? Instead of 9 4, it became 9 9. So how it happened was, initially we can explain that using a box and circle diagram. So if you have y in main, so you declare y, then you put the value of y as 4, then you do test y. So whenever you do test y, there is that formal parameter int ampersand x, right? So x gets associated with the location of y. That is passing by reference. So instead of creating a new location for x, when you pass by reference, you just point x to the same location of y instead of creating a new location. That is the difference between pass by value and pass by reference. Pass by value creates a new location, new variable, new box and circle, right? And just copies the value of y into x. But pass by reference doesn't do that. Pass by reference doesn't create a new location. It just associates the location of x to location of y. So now if you change x, basically what are you doing? You're changing that value in y. Right? So since you're changing that value in y, when you do printf, when you come back, you lose the scope of x. So x deletes, fine, but y's value is 9 now. Right? So when you do print y, you get 9. So the output becomes 9 9. And that is passed by reference. Now we come to pass by name. It's very weird. So formal parameters are replaced by the text of the actual parameters everywhere in the function. So this is textual replacement. Let's take an example. So what does it mean by textual replacement? So that's the int main function. So int you have a new variable y equals 4, then you did test y. So if you do textual replacement, what you will have to do conceptually, what you can do is that you can take this test function and replace all instances of x by y. Right? What you did? You took the test function, all instances of x are replaced by y. Very weird. No programming language does that. Right? C definitely doesn't do that. Now what is the value? You still get 99. Because why? Because now you have changed the value of y. Y became y plus 5, so y became 4. So you print y, which is 4. Now, since you have done a textual replacement, so that means that y variable is the same y variable as main. So that y variable's value has changed to 9. So you print 9 again. Let's take another example. What happens to this if you pass by name? So what do you have? You have I equals 1. I was a global variable. A10 is an array. I equals 1. A1 is 1. A2 is 2. Then you call that increment function AI, and there you increment I, and then you increment X, and then you print all those. Can you take 1 or 2 minutes to try and just to attempt to see what will be the output by doing passing by name? So what do you have to do? You have to take that function in, right, increment, and replace all the instances of x by AI textually. So if you do that, what will be the output?
Two, one, three.
What?
213.
213.
Yes.
Why?
Well, because since you're replacing x and inc with a of I, and I gets incremented before x gets incremented, the new AI, instead of being the a of 1 from earlier, it's now a2 because of that increment.
Okay. So let's see. He says the output will be 213. So let's go ahead. So you have the inc function. So every instance of x has to be replaced by AI textually. So I plus 1, then you have AI plus plus. Right? So now when you call inc AI, you had I equals 1, A1 equals 1, and A2 equals 2. Now you execute that function. You made I plus plus, so I became 2. You made AI plus plus, so what is I? I is 2. And what is AI? So A2. So you made A2 plus plus, so A2 became 3, right? You get this 213. Extremely weird, right? So that is pass by name. Do you have any doubts? Anybody has doubts with pass by name? Let's take another example. What will be the output here? Pass by name. So in int main you call q. Q doesn't have any arguments, so you're lucky, right? So q comes here, then int j equals 2, then I becomes 0, I is global, right? And then you do pi plus j. Now pi is that int y. What do? This is another extremely weird case. So do the same thing. P is being called with an argument, so you have to textually replace P. So you are basically doing P int I plus j. So now int j becomes int I plus j. Then I plus plus, then you return j and I plus j. Now which j is what? What is the value of j there in that function? Does all the j have the same value? So which j has what value? So inside that function p, you have declared a new j, right? And you have called p as pi plus j. Now what is which j?
The j and I plus j equal 2 from q.
So j and I will be 2, then in I plus j, that j will be 2. And this new j should be a separate variable, right? Because you have declared it in that function. So this j has to be 2 plus 0. This j also has 2. Right? Now you do I plus plus. I became what? 1. I became 1. Now you do j plus I plus j. So j was 2. What was previous j? Previous j was also 2. 2 plus 1, 3. And then plus 2, 5. So you should return 5. Do we have that result? Yes, we have that result. Luckily. So now what is the rule? The rule is that if you have a j declared inside that function and you still pass by name using j, then these two j's are different. They have the same name, but they resolve to two different values. Right? So that is the problem with pass by name. It becomes extremely confusing. Another example. What do you do here? What is the output? Again, you follow the same steps. So you are calling the function foo. So you make you do textual replacement. So that is the function foo. Now what is the output?
1,
Will it be 110? Or will it be 010?
0,
010.
10.
Turns out it is 010. Because you did textual replacement. So you didn't execute A++. A++ is just a text. That is the problem with pass by name. Right? You do it, if that was C, you would have done A++ and would have made A equals 1. Because you are passing by value. So if you are passing by value, you have to compute the value of A++. Right? If you don't compute the value of A++, you cannot pass by value. So since C does pass by value, it will compute A plus plus. And if it computes A plus plus, A plus A becomes 1. Then you will have the result 110. But since I am doing pass by name, I don't need to compute value. I just do textual replacement. So I did textual replacement, so that means I did not compute A plus plus. Now inside there, test is not being used, so you just return the value 10. So A is not incremented, you get 10, so the result is 0, 10 instead of 1, 10. Do you understand these problems with pass by name and the characteristic of pass by name? Let's see another example. Oh, this is the same example. This is the same example that we did. No, this just explains uh, how you can implement pass by name using C. How can you implement pass by name using C? So what will happen? Why do we need to know that? By doing that, we will understand what is the characteristics of pass by name. How can we define the exact operation of pass by name? So this is a C implementation which is equivalent to pass by name of this implementation. So what are we doing? Here what we are doing is the int main remains the same. So the main remains the same. Then we have to implement q. Void q, the function itself has no input arguments, so that remains the same. Then instead of calling pi plus j, we define a new variable called I plus j. Right? Because we have to now emulate the action by having pass by value, by using pass by value, and pass by reference. So by using pass by value and pass by reference, we have to implement this. So we declare a new variable. We make j equals 2, and we make I and j both as global. Instead of having I as global, we make I and j both as global. So we make j equals 2, I equals 0. So what does I plus j become? So I plus j is another function. I plus j is another function which just adds up I and j and returns. And it just adds up I and j and returns. Now we have to replicate the function p. So in p we do this. We try to. So the p takes an argument, which is a function. Right? The argument of p is now a function, because you know p we called p as I plus j. So I plus j is the function. The argument of p is a function. So what do? We say that if j equals y, then we do I plus plus and we return j plus y. If we do this, then we will have pass by name. How or what is the intuition behind that? Why did we have to do this? Let's try to understand. So what happened in pass by name? In pass by name, what is happening is that we are doing textual replacement, right? So by textual replacement, what we are doing is we are taking the function p and replacing it by I plus j. Taking the function p and replacing all y by I plus j. Now, what is I plus j? I plus j is an expression, right? I plus j is an expression. So that expression can be computed using a function. Right? It has to be computed using some function. So that's why we declare a function called I plus j. That function, what is the purpose of that function? The purpose of that function is whenever you call it, it adds up I and j and returns that value. So this textual replacement is being mimicked by using a function. Because by doing textual replacement, we did y, we replaced it by I plus j. I plus j is an expression. That expression can be computed by a function. So that's why we took that decision. So now P, instead of taking an integer as input, takes a function as input. Right? Now what does P do? P does j equals y. Now what is that y? That y is the computation of that expression I plus j. So that should be the return of value of the function. So that's why in P we have j equals y. Oh, no, y is the function now. Right? So what is y in that particular instance? Y becomes the function I plus j, and which returns the value I plus j. So then we do I plus plus, and then return j plus y, and this y is again a function. So if you think of that, if we replace y by that I plus j function, that's basically what it is doing. If you in your mind replace y by I plus j function, then you will see that that is same as passing by name. Do you understand this concept? Just in your mind replace that y in that second representation. Just replace the y function by the I plus j function. If you do that, then this code is exactly same as pass by name. Now you have to make I and j global. Why? You have to make j global because j's value 2 has to be accessed by I plus j as well as p. So that's why you make j global. That is a trick to implement pass by name using value. So what you do basically, what is the rule? How to implement pass by name using pass by value and reference? All the local variables, make them global. That's the first step. All local variables, make them global. So you make j global, you make y global, and all those things, right? So all the variables you have made global. Now what you do is whatever textual replacement you have to do, define a function for that. So you had to do I plus j, you have to do that textual replacement. You define a function I plus j. What does that function do? That function computes the expression that you have. Right? The function computes that expression. Now, whatever function you're calling, doing pass by name, change its argument. Change its argument and make it a function. Instead of an integer, make it a function. And while you are calling that p, you give that expression function as input. We will exactly identify what are the rules maybe next class. We'll write it down. We'll write down the rules, how to implement pass by name using value and reference.